Draw the skeletal formula of 3-methyl-butanal. So but is 4, so you've got to draw 1, 2, 3, 4 in a line, in a zigzag shape, 4 carbons in a line, so 4 lines. The butanal has got a C double bond O with an H on it. You don't need to draw the H, so you're just going to draw a double bond O. Butanal, the aldehyde group is always at carbon number 1, so you count along the chain and then put another branch off a line at number 3. Let's have a look how that looks. So let's go through it again. 4 in a line for but, 1, 2, 3, 4. This is your aldehyde group. It's the carbon there that's got a double bond O, and it'll have an H off it as well. So it's CH double bond O, a CHO group, CHO. You don't need to draw the H, we're leaving all the H's off. But one thing you need to recognize is that this aldehyde group is at the end of a chain, so that's always carbon number 1. So your methyl group's at carbon number 3. 1, 2, 3, and there's your methyl group. It can either go up or down, doesn't really matter. And that's your carbon, not showing its hydrogens, of the methyl group. Draw the displayed formula C5H11Br that's the major product of the reaction of 2-methyl-butyene with hydrogen bromide. So to show this, we need to do the mechanism and show you what it looks like. So here, this is your 2-methyl-butyene. 2-methyl-butyene, let's just check. But 1, 2, 3, 4 in a line. 4 in a line. 1, 2, 3, 4 in a line. And at carbon number 2, if I start labelling this as carbon number 1, carbon number 2, I've got a methyl group and I've got a double bond at carbon number 2 as well. I could put this methyl group here instead if I wanted to. But I've got 4 in a line at carbon number 1, 2 at carbon number 2, I've got a double bond and I've got a methyl group. So that's 2-methyl-butyene with hydrogen bromide. Now the HBr is going to join across here. The question is, the HBr, when the H joins on, does it join to this carbon or does it join to this carbon? Which way does the H join, this one or this one? Well, the rule is that a H bonds to the carbon that's already got the most H's bonded to it. This carbon's got one H bonded to it, this carbon has got no H's bonded to it. So the hydrogen will bond to this one, and that's to do with the stability of the carbocation that's formed. It's going to end up with a tertiary carbocation here. But just so that you can get it right, the H joins onto here, and the Br then will join onto the other one when Br minus with a lone pair. The lone pair is going to join onto the C plus that's there. So that's what it's going to look like. That gets you the marks. You don't need to draw this bit. This is what gets you the marks for recognizing that this has got an H and this has got a Br in the product. Thermal cracking of hydrocarbons produces molecules that are attacked by electrophiles. Sorry, I've drawn the carbocation there. Once the H joins on the carbocation there, and the Br minus is going to join onto here. Draw the structure of one of these molecules that contains 4 carbon atoms. Let's read through it again. Thermal cracking of hydrocarbons produces molecules that are attacked by electrophiles like HBRs, because they have a region of high electron density. Draw the structure of one of these molecules that contains 4 carbon atoms. High electron density means it's got a double bond. That's another way of saying that it's got a double bond. And electrophiles like HBRs will attack by electrophilic addition onto that double bond. So thermal cracking produces molecules 4 carbon atoms with a double bond. So 1, 2, 3, 4 carbon atoms with a double bond. The double bond can be here or it could be in the middle. Doesn't really matter. So it could be but-1ene or but-2ene.